Welcome to Biochemistry Literacy for Kids, Lesson 5. This is a great lesson. It's a favorite lesson in the classes that I've taught because we get some really cool applications of these covalent bonding concepts. Before we get started with new material, we're going to review the homework from Lesson 4 because it's really important that these concepts from Lesson 4 are very solidified before we go on. Here are some answers for your organic chemistry drawing practice. We have N2H2. That's what the structure should look like. There's only one way you can draw N2H2. And remember to draw those lone pair electrons also. If you don't remember why is there only one set of lone pair electrons per nitrogen, definitely go back to Lesson 4 and redraw those atom diagrams and review the structure of ammonia. It's really important that you understand where those lone pairs are coming from. We're next going to do H2O2. This is peroxide. That's the only way to draw that structure. We have the next one, which is methanol. Only one way of doing this one too. If you draw the carbon on the right or the carbon on the left, it doesn't make any difference because it's a three-dimensional object, so it can be turned, right? So if you drew the oxygen on the left or oxygen on the right, doesn't make any difference in chemistry. You'll get used to looking at things upside down and backwards in chemistry. It's not like English or any other language where things have to be in a certain order necessarily. All right, these a couple of these questions here have several answers, and this means we have what's called an isomer. Isomers are molecules that have the same formula but different connections. The atoms are connected a little bit differently. So many people will do the structure on the left, some people do the structure on the right. Those are both answers for this particular formula. They're totally different molecules though, but they would both be considered right in a college organic chemistry exam actually. The next one, CH2Cl2, there's only one way to do this. And again, if you drew the chlorines on the bottom or on the sides, it doesn't make any difference in this particular case. What you can do is you can always make the model of these and see if there's any difference in putting those chlorines in one or the other position. There's more to say about a molecule like that, but we'll leave it until a couple lessons from now. All right, and the last one, C4H10. Some people may have done this one. This is the simple solution for this particular one, but that's also a solution. It's more of a branched version of this molecule. And let's look at the names. Let's look at the bottom right corner one here. We have butane, which is the hydrocarbon to the left, and then we have isobutane, which is an isomer of butane, and it has a sort of a different arrangement of the carbons. All right, and the other part of your homework was to draw the atomic version of the structure of C2H4, and you should have come up with something like this, showing all the orbitals and the shared pairs of electrons. Remember that a double bond is two shared pairs of electrons, so we should see something like that. That's going to be really helpful for us in this lesson because we're going to be doing some virtual chemical reactions with ethylene in just a couple minutes. Here we go. All right, so we're going to look at a really, really famous chemical reaction, just kind of a basic version of this reaction. It's the polymerization of ethylene to make polyethylene in just a few minutes. So let's look at first the formation of ethene. All right, so that kind of should make sense to us based on what we've seen before. We see that the two carbon atoms can bond in a double bonded kind of fashion. This leaves 4 extra unbonded electrons that need a buddy, right? So hydrogens are a perfect partner for them, and we end up with the 4 hydrogens being added right there. All right, and that's what the model looks like. So if you have not done so, take your model kits out and start building this. Although if you're doing this in a big class, you may want to wait to present all this and then have them do this a little later when you can let things get a little noisier. All right, so this is our structural picture of ethylene that we know right there, right? What we're going to do is look at a new concept. So this new concept has to do with a chemical reaction. We're going to combine ethylenes together, or ethylenes together, and to do that, it's a free radical reaction. So what is a free radical? Free radical are lone electrons. So what certain conditions can cause paired electrons to unpair like that. All right, and that's a whole nother story how this can happen. Another molecule is needed for this to happen. But just for now, for simplicity's sake, trust me that the one of those shared pairs of electrons can unpair. Now this should look really bad to you. This should scream, oh, these lone electrons, this is they want to form a bond with something, right? This is not what we're used to seeing, lone electrons kind of hanging out by themselves. When this is done in a reaction, we're going to have more than one molecule that is becoming radicalized, right? There's going to be radicals or free electrons everywhere. Now we can probably predict what's going to happen, right? Because we've been seeing it for a while now. Those lone electrons are going to repair and form a new bond that wasn't there before, a bond between two different ethylene molecules. And please go ahead and draw. The more you draw, the better in chemistry. Draw. That's how you let these concepts sink in. All right. So what we've done is we've polymerized. Okay. So what is polymerization? It's the repetitive reaction or creating a repetitive bonding between different molecules. So we formed a very short polymer, but we did form a polymer. Let's look at some of the Greek words here. Poly means many. Mer more or less means part. So a polymer means many parts. A monomer would have been those are monomers, right? Probably before we radicalize, right? Like, so that's a monomer. That's just one molecule. But when we do this reaction where we cause two molecules to come together, that's where we've made the polymer. All right, so once the students are familiar and they kind of get an idea of what this polymerization concept is, this radical polymerization concept, we want to have them figure out a way to build the polymer so they can see what a polyethylene molecule is. They can understand this polymerization concept. We can't really make a metaphor for single electron events using the MOLYMOD kits because the bonds, remember what's a bond? A bond's a shared pair of electrons. So unless you were to kind of saw the bonds in half, you wouldn't really have a single electron. So we can't totally simulate radical polymerization, but we can still make a polymer. We can still make a polyethylene polymer. So to do that, we're going to look at the images on the bottom here, these two structures here. What you're going to do is have each student make an ethylene molecule, and you're going to have people pair up. So you're going to have two ethylenes next to each other. What they're going to do is they're going to pop off one of those flexible bonds so that we have the ability to form a new bond, which is kind of the polymerization idea. Then the students are going to kind of connect those two ethylenes together, and they're going to make, maybe you call it diethylene, a dimer of two ethylene molecules. That group will find another group and connect that set of ethylenes with more ethylenes, and it'll get longer and longer. If this is done in a big class, it's a really impressive activity, and the kids really get this polymerization idea, and they want to take pictures. It's just such a fun thing to do. Before you do that, you might want to show them this picture, which shows them kind of what to expect, right? You're going to see a really long carbon chain, hydrogens everywhere. This is the polyethylene polymer. That's what they're going to be making. All right, so what's the significance of polyethylene? Polyethylene is used to make most of the plastic stuff in the world, okay? So the one that everyone's familiar with is a gallon of milk that is made of polyethylene. There's two different kinds of polyethylene that have different recycling symbols, right? There's the high-density polyethylene, and there's low-density polyethylene. Okay, if you study polymer science, you could learn more about what that means. There's also a lot of other kinds of plastic, which maybe we can do another lesson on. A whole lesson on plastics would be fascinating. Anyway, how is it possible that ethylene, this little molecule, which is, by the way, it's a gas. Ethylene is a gas because it's so small. How does a gas molecule become a solid, a plastic solid molecule? It's because the molecule is so long and so heavy. It kind of makes sense that the heavier the molecule is, the more solid it becomes. So this is kind of a Pymol rendered picture of a polyethylene chain. And it's not just one chain, right? It's probably, it's billions and billions of polyethylene chains, which all pack together to make the plastic material. So this is kind of a rough visualization of what polyethylene is. If you look at just look up some statistics on polyethylene, one number that comes up is there's 100,000 carbons in every polyethylene molecule. So every time you polymerize, you're doing this, tens of thousands of times to make enormous molecules. All right, so after the students do this polyethylene plastic polymerization reaction using the models, we're going to move on to another, the second half of this lesson, which gets into the idea of chemical literacy. So again, we're remembering this 4-3-2-1 rule. There's this corresponding idea between the number of bonds that an element can form and the number of lone electrons it has when you build their electron orbitals. Carbons have 4 lone electrons, right? Therefore, they always make 4 bonds. That's going to be really, really important in decoding professional chemistry structures. So this is the kind of structure you would see if you looked at a chemistry textbook or looked on Wikipedia and or anywhere online, you were learning about a new molecule. That's what you're going to see, okay? You're not going to see carbons drawn out. The reason you're not going to see carbons drawn out is because they're so common and you're assumed to know that every carbon makes 4 bonds. So I'm going to show you how to read this structure, and we're going to draw this a lot. We're going to get a lot of practice looking at these professional structures and going back to something more basic. Whenever you see a structure like this, you're going to want to take at least in the beginning, take all the angles you see between the bonds and all the kind of terminal bonds. Everywhere you see a line extending, you're going to draw little black dots, just like you see here, okay? So wherever you see an intersection of a bond, and also wherever a bond kind of branches off, draw those black dots in. Those black dots are the carbons. If you want to draw it another way, we can draw all the carbons in again. That's the kind of more simplified version of what this professional drawing is trying to say. All right, the molecule that we're working with here is some kind of anti-arthritis medicine. It's nothing particularly famous, but it's a cool molecule because it has all the elements that we've been talking about. One thing that we may be missing here that we're not sure where they are, where are the hydrogens, right? Most of the molecules we built are kind of encrusted in hydrogen, so we don't see any H's here. So where are they? The hydrogens take up the extra bonding positions that are required for every carbon, right? So we see many carbons. If you look on the simplified structure on the right here, there's a lot of carbons that only have 3 bonds or that have only 1 bond to them, for example. We know that carbons always make 4 bonds, so we have to add those hydrogen in mentally. We can also, before we get good at that, we can draw them in. So what you're going to practice doing is you're going to practice finding all the carbons and adding in the hydrogens. This is done in the imagination of every chemist, but when we're starting, if you take a college organic chemistry class, this is actually a real exercise we do to get us, remembering what's going on here with how the nomenclatures look. So that's the one on the left. The middle one, same deal, right? We're adding in hydrogen. So for example, the carbon that's kind of the single carbon at the bottom here, that one requires 3 extra bonds, so we add 3 hydrogens. Hydrogen is just what we assume is there when we don't see any extra bonds. Many of the carbons require 1 extra hydrogen. The structure on the right is the easiest to see, right? We see carbons that have maybe 3 bonds. We've got to add 1 more bond to it. That bond is always taken up by a hydrogen. This is just the convention in organic chemistry. When you look at these professional structures, this is what everyone should be doing mentally, realizing that there's actually a lot of other atoms there that are not necessarily written there. There's also a convention that if we see nitrogens or oxygens, those hydrogens tend to be written out, whereas carbons, we omit them. It's because carbons are so much more common. You can imagine trying to draw out all these hydrogens all the time. It just would be a huge mess. So this is why we we draw the structures like the one on the left here. That's why chemists will do that. All right, we're going to now get a little bit more practice. This is the next kind of set of drawings that I would recommend that the students copy over and then practice adding in those hydrogens. So we'll go to the worksheets for those. These are the flavors, right? Before we looked at a drug, now we're looking at flavors. We have the flavor of banana, vanilla flavor, rose flavor. We have the flavor of grapes, coconut flavor, and we have the wintergreen, kind of a minty flavor. In a few minutes, we're going to be looking at a lot more flavors, but for right now, we're just using this exercise to practice this idea of where do the hydrogens go, right? So how do we look at what the structure really is? The top 2 structures have this very simple nomenclature. The middle ones show you where the carbons go, and then the bottom ones are the professional ones, the ones that I would write if I was kind of drawing something out. But as chemists, we can get into this nomenclature, like understanding what all these three different versions of the same thing mean. So this will take a while for the students to do. Look at every carbon, make sure every carbon has 4 bonds. If it only has 1 bond, you have to add 3 more bonds. If it has 3 bonds, you have to add 1 more bond. You got to have 4 bonds every time. If a carbon already has 4 bonds, don't add any hydrogens to it because it's written out fine. You can't have 5 bonds to a carbon. So here's the answer for the first one. This would obviously take students longer to figure out. There's the one for the grape flavor. Vanillin. Right? This one I'm including some oxygens there just for fun. We have several hydrogens that have been added in here. This is the coconut flavor. We have the rose scent. So what I would recommend is actually, highlighting where all the carbons are, and then adding in the hydrogens. That can be helpful. That's how I learned in organic chemistry how to recognize what these structures mean. And then for this one, this has a cool ring structure in it. They're just double bonds though. Just don't worry about the ring too much. Add in the carbons to wherever you see a joint or an end, and then look at the carbon. Does the carbon have 4 bonds to it yet? If it doesn't have 4 bonds, you have to add more bonds, and it's assumed hydrogens go where those extra bonds are. So now we're going to begin one of the really, really fun activities. This activity, kids want to kind of do an extra day or two of this activity because it's so much fun for them. We're going to look at the chemistry of flavor molecules in detail. So here's a whole panel of flavor molecules. These are just different molecules that give certain foods their aroma. So it gives us the sense of what the food is. So for example, the molecule on the top left here, pentenyl pentanoate. This is the signature molecule that gives apple flavor its aroma, right? There's a lot more in the names here than we're going to have time to do here, but you can kind of make the kids look at it a little bit. Pentenyl pentanoate, what could that possibly mean? What's pentenyl mean? Maybe like pentagon, 5, right? What you'll notice is that there's 5 carbons on the left side, 5 carbons on the right side. We're not going to go over all the organic chemistry naming, but there are certain patterns you might see. Also, looking down, we see octyl acetate, right? What's octyl mean? Maybe octagon, 8. 8 carbons are on the left side of this molecule. So there's a whole nomenclature scheme that we have to learn eventually. But for now, we're just kind of looking at this from a structural perspective and just kind of a big picture thing. So don't worry too much about the names. These are all molecules that are giving mostly fruit flavors, right? We see apple, rose, we have grape, we have strawberry. We're going to look at the significance of this. Why are these all fruit flavors? But before we do that, we're going to start to just kind of decode what they are. So, right, I drew these in the professional nomenclature, right, without any carbons, without helping at all. The first thing that you're going to have the students do is have them pick a few of these, ones that they might be interested in constructing with the MolyMod kits, and add in all the carbons that are needed to fully interpret the structure. And don't show them this right away. You can show them just like the idea of what they should be doing. But definitely it's important for them to go through and kind of add in the black circles to show where all the carbons are. That'll help them be more successful when they try to when they attempt to construct the molecules. They'll get what the structures mean. And now we remember that every time we see one of these carbons, we have to add in extra bonds because carbons always have 4 bonds. And we assume in chemistry that those extra bonds are taken up with hydrogens. So I kind of highlighted a few of these here, just not to overwhelm the slide here. But this is what you would have the students do. If the students were going to pick peach flavor and lemon flavor, have them create those add-ons to those structures there. So once they've added on the carbon dots and the hydrogens with their bonds, they're ready to create with the MolyMod kits their first flavor molecule model. And it's definitely a little bit of a learning curve for some of the students. They have to kind of connect the dots and realize how the picture corresponds with reality. And that's fine. It's going to take them a little while to figure it out. And if you have them work together and if you kind of supervise, they will all get it eventually. They will start to connect the nomenclature to what the 3D molecule is. And they'll be getting lots of more practice with this. So this is just a way for them to get their feet wet into some more complex chemistry model building. There's a lot going on here with these flavor molecules. One cool thing to point out is this first, what's called functional group. It's chemical phrase. It's kind of like something that we see over and over again that has some certain significance. It's an ester, okay? Esters are a pattern of atoms that are bonded together. An oxygen bonded to a carbon, which is bonded to a double bonded oxygen. That's called an ester. If you have them look through this panel here, you'll find that actually a lot of these molecules are esters. What are esters known for in the realm of flavors? What do all these esters have in common, except for maybe the wintergreen? These are all fruit flavors. Esters, for whatever reason, are perceived as a fruit flavor to us. It's really interesting to kind of ponder like why that is, but this is just the reality that we are chemical sensors. We can tell if a molecule has an ester in it, which I find is a fascinating thing. Let's look at a couple other things. There's another functional group, there's a lot of functional groups here, but the other one that I want to point out is the aldehyde, okay? Aldehydes are kind of like esters, but instead of one of the oxygens, what's there instead? A hydrogen. There's a hydrogen there instead. Except for the vanilla, let's look at the ones on the bottom. What do all those molecules have in common at the bottom with the green aldehydes? They all have actually a vegetable-y sort of a flavor to them, right? Tomato, avocado, watermelon is a fruit, but actually when you think about it, watermelon really has a bit of a vegetable-y kind of squashy flavor to it when you really think about that. Aldehydes are perceived as vegetable flavors. Also, the other famous aldehyde is there's molecules that are associated with freshly cut grass, and those are also aldehydes famously. So what we're seeing here is that we are chemical sensors. Like we can actually tell what atoms are connected to what in certain contexts, which I think is amazing. All right, going to this next panel of flavor or odor molecules, we're looking at a whole new set of molecules here. They look different. What they are is different, right? We don't see too many fruity sort of flavors here. We see things like parsley, citronella, thyme, oregano, cumin, mint. These are spice flavors, right? We see when we add the carbons in, we see that we have a few different patterns here. We have kind of these chains, these kind of branched chains of carbons. We have rings of carbons, and we have the fancy ones on the bottom right here, which are double rings of carbons. Really different from what we saw before, right? Isn't it interesting that this kind of plan, this molecular plan, is sensed not as a fruit flavor to us, but as different kinds of spicy flavors. And lemon, when you think about it, lemon is a fruit, but it's really like a spice also. It's a really strong flavor. It's something really a little bit different from maybe what we would associate, maybe like an apple is really different from a lemon flavor. Lemon might be a little bit closer to maybe like a minty or like a rosemary kind of flavor. So we start to see why that is, because the way we sense our flavors has to do with the chemical structures. So things that are structurally similar may be sensed similarly. Not always, but it's gives us a framework to think about it. So these are different molecules that we can also give the students a chance to build, just for some variety here. There's an amazing pattern, which I always like to highlight here, among all these flavor molecules. So this is actually giving away the hint here. What I would like the students to do, and whenever I teach this lesson, is to have the students figure out, is there a pattern in all the things that we're looking at here? Is there something that unites all these molecules together? And it might take them a little while to think about it, but there's usually at least one person who eventually figures it out. There's probably more if you give them more time. The one thing that unites almost all these molecules together is the fact that they all contain 10 carbons. That's right. A spice molecule almost always has 10 carbons in it. Just count them up if you don't believe me about it. Why is that? That things like menthol, mint flavor, citronellol, lemongrass flavor, even these pinene flavors, right? These really strange ones, they all have 10 carbons. How can that possibly be? Is it some kind of, strange pattern of nature? It actually has to do with the fact that the molecule is made from a polymerization. It's made from two molecules that are called isoprene. Isoprene is a really famous molecule, actually. Isoprenes have 5 carbons each. So when you connect them to each other, in a special kind of reaction, you get something that has obviously 10 carbons, not 5. 5 plus 5 is 10. We can then do things like change the double bonds. We can add on oxygens. We can do things like that. We can also cyclize the thing and make it into a ring structure. So if you can actually have the students create this double isoprene and then cyclize it, you'll end up with things that look like maybe menthol. You can add another cycle, just create another bond between 2 more carbons, and you'll end up with things like the camphor or the pinenes down there. But this is the truth, that isoprenes, these are actually all these molecules are called isoprenes because they come from isoprene itself. Really cool pattern of nature. Spices usually have 10 carbons because they're made of an isoprene polymerization. So really, really cool. We can look into the mechanism of that. How is it that these reactions happen? That's a little bit more of an advanced topic, but just remembering that one cool fact I think is really a neat takeaway from this lesson, that spices tend to be made of isoprenes. Finally, the last thing that I'll say about flavors, and by the way, we don't know much about flavors, like how do we actually sense them, the science behind the sensation of odors is not that well studied yet. It's a very difficult topic apparently, but we can know about what molecules consist of a certain fragrance. Many fragrances are not single molecules; they're actually combinations of molecules. So while a artificial orange flavor, like you get in like an orange starburst, might contain octyl acetate, the real natural orange flavor actually is a mixture of many different molecules. And actually the main molecule apparently in orange flavor is limonene, which is an isoprene, right? It has 10 carbons there. The octyl acetate, which is the kind of prominent ingredient in orange flavor, is actually just a small amount. And we see actually a bunch of other stuff that makes up a orange flavor. So the idea is that the perception of a flavor isn't just one molecule. We actually sense many different flavors, many different molecules at once creates a flavor, which is a cool thing to realize. It's kind of like, how do we hear a sound? Like sounds aren't just some kind of pure tone. They can be mixtures of things. Gives us the sound of a certain person's voice. Like how do we recognize that voice? So maybe that's the kind of analogy you could use there. Pumpkin spice. For some reason, students were always asking me, what is pumpkin spice? So I just made this little caption here. Pumpkin spice is made up of a bunch of different spices. Here are the molecules, some of the main constituents of these molecules. Cinnamaldehyde is a very famous one. It's an aldehyde. You might see that aldehyde there. That's the main flavor of cinnamon. We have eugenol, which is part of what cloves and allspice have. And then the nutmeg flavor is this very strange molecule with 2 rings in it, this one triangular ring. By the way, one thing that came up on the other slides, which I didn't talk about, these solid wedges and the dotted wedges, the kind of little dashes here, this has to do with how the carbon or how the part of the molecule is angled in or out. So we have a whole unit on this later. But as the students are building these molecules, if they choose to build one of these, they'll notice that they come up with these, there's sometimes a choice where they have to build, does the carbon point up towards them or away from them? That's what these wedges are meant to be. So the solid wedges are pointing towards you, the dotted wedges are pointing away. But we have a whole nother lesson on this. I just included it here for simplicity, for completeness. Don't worry about it too much with the wedges. The wedges are just bonds, okay? Right. So those are some interesting flavors. And by the way, the pumpkin spice flavor, we sense all those spices together, gives us this pumpkin spice perception. What about nasty smelling molecules, right? What about rotting flesh or some kind of putrid fishy smell or other things, right? These are some options if the students want to build a disgusting or gross molecule, and a lot of kids want to build this. Some of them do not want to build these, which is really funny. They do not want to build something that smells bad, even though they know it won't actually smell like anything. Cadaverin is, just like the name suggests, the smell of rotting flesh. Okay, putrescine, that's another nice name. Some of these other molecules have fishy smells or other kind of gross smells. What do they all have in common? What they all have in common are obviously the nitrogens. Nitrogens are not always, but often a sign that a molecule has a stinky smell. And why is this? it's amazing why this is. If we know a little bit more about chemistry, which we will later, we're going to realize that molecules like cadaverine and putrescine, they come from the rotting or the breakdown of proteins and amino acids. These molecules are a sign that whatever you're smelling is rotting flesh. So you would obviously animals would, at least animals like us, do not want to eat rotting things because we'll get sick. So we have the sensation of something being gross smelling if we smell these molecules. Same thing for the indole. Okay, the indole is also a sign of broken down proteins that are not really probably safe to eat anymore. All right. So that's a cool, another awesome connection for the students to make. Here's just some carbons added in if they needed some review and of how that works. And remember, whenever you see those 10 carbons, you have an isoprene, something that it probably's got a spicy flavor, and we see that in a few of these molecules over here. All right, and then the final thing I like to do in this lesson to kind of sum up this idea of chemical literacy is to have them correct some misdrawn structures. So these are two structures that are not drawn correctly, and if they've started to have these concepts sink in, they'll have the chemical literacy to correct the structures. So what's wrong with the top structure? Look at each atom individually. What you see, one of them is not possible. The carbon here is not possible to be that way. It can't have 5 bonds because we know that there's only 4 outer electrons that are unpaired in a carbon, so there's no way to make 5 bonds. It's impossible. So have them correct it. You get something like this. The bottom one, as far as we know, it will change later, but nitrogens don't make 4 bonds at this point. We got to fix those. So what can we fix it with? How can we correct those structures? Just changes the carbon. Everything's fine now. If they can do things like this, it shows that it's really sinking in what we're doing here, and they're going to have a much better time looking at advanced structures, complicated biomolecules and things like that. These two molecules here, I picked them just because they're pretty significant. The top one is glycine. It's the most simple amino acid. The one on the bottom is oxalic acid, which is what gives things like star fruit their sour flavor. Star fruit is kind of a unique family in that it produces oxalic acid and not a lot of citric acid, which is the main acid that's in fruit. And then finally we have, this is a little bit unfortunate, but we can see that we really are doing college work here, even though we may be in elementary school. These are, unfortunately, these are actual quizzes. These are not from my students, but they're from some other college students that had a quiz on this same material that we're doing now, and they're a little bit confused still. So we can see that many of the students will actually have a laugh looking at these and correcting them and realizing that they're actually learning the same things that college kids are learning, and they can correct some college kids' work. So what's the first one? What's the first one trying to be here? It's obviously a kind of a mess, but that carbon's got way too many bonds, right? You can't have 6 bonds on a carbon. So they were trying to make CO2. That's what it should be. The next one, they were trying to make something. They were trying to make CF4, but it's got to look like that. They didn't have the right amount of lone pairs on the fluorines, right? If you remember from the last lesson, fluorines have 3 lone pairs each, and we understand why that is now. And the bottom one is the funniest one. Really makes no sense. You can't have hydrogens with 2 bonds because hydrogens only have 1 electron. So how could they make 2 bonds? This one they're trying to do water, obviously. So that one's just totally wrong. So this is like this, and I would encourage them to correct these and to correct each other's structures too. That's a great way. Sometimes the kids will do a great job, maybe make 1 or 2 mistakes, and then if they work together, they can correct each other if they're trying to make new things. So at the end of lesson 5, I like to actually encourage them to draw their own structures, make something very large and creative, even. To show that they're getting this chemical literacy concept. All right, hope that this is working well for you, and we'll see you in lesson 6.